Swayam Prabha. Digital India. Educated India.
Welcome back. In the previous videos we had seen how to use logistic regression for multi-class problems. We had done that using a softmax function, if you remember. We had also looked at what the corresponding loss function was, etc. In this video I want you to see a simple schematic which will also tell you how exactly a matrix comes when you deal with weights with multiple classes, when we have multiple classes in multinomial logistic regression. So, let us consider a simple example. Let us say I have 3 input features and let us say I have 3 output features also. Y1 hat, Y2 hat, Y3 hat. So, let us say this is a 3 class classification problem. You can think of multiple examples for this. For example, if I give height, weight and age, suppose you want to find out whether this person has no probability of heart disease or low probability of heart disease, medium probability of heart disease or high probability of heart disease. This is not quite a classification problem, but just as an example I can give you this. We will look at several examples or at least a few examples in the examples week, which will be around week 9 or so. So, you can think of any convenient example for yourself, and now let us introduce our usual bias unit, which is 1 or x naught, and now we want to find out what is y1 hat, y2 hat, y3 hat. So, the portion that we are doing right now is the forward model. Okay. So, as usual y1 hat is equal to softmax of the linear combinations of this W0 plus W1 x1 plus W2 x2 plus W3 x3. Okay. That would be y1 hat. Now, suppose I have y2 hat. Now, y2 hat is also softmax of some linear combination W0, let us say, plus W1 x1 plus W2 x2 plus W3 x3. Now, suppose this W0, W1, W2, W3 were the same in both these cases, obviously you are going to get the same y1 hat as well as y2 hat, okay, because otherwise the functions are identical. So, this is not a good idea. So, you need different weights. So, we are going to use different weights here. So, we need some terminology in order to distinguish these two weights. So, I will call it W01, W11, W21, W31, where the 1 stands for the output and the 0, 1, 2, 3 actually starts for the input. Similarly, you can easily see that now this should be W02, W12, W22 and W32. Finally, if we come here, I need another set of weights. Okay. So, y hat 3 would be softmax of W03, W13 x1, W23 x2 plus W33 x3. Okay. So, how many weights do we have? 4 unique weights in each one of these. So, you have 4 into 3 12 weights in order to account for the bias term also. So, how would we write this matrix wise? So, we have x vector which was 3 cross 1, we have y hat which is also 3 cross 1, and we have w which is now a weight matrix. You can see w has 2 indices. W I j has I is the input feature and j is the output feature. Okay. You had also seen in the earlier video with XOR that you could have more than one layer. In that case, typically we add an L here which denotes the level. Okay. So, you could have Wij1, Wij2, Wij3, etc., etc. So, you will have multiple weights. So, this is the large number of weights, as you will see in the videos in the next week. When we come to convolutional neural networks, you have millions and millions of parameters in usual practical neural networks that sit in today, which is why they are extremely powerful. Okay. Coming back to this, if we want to write y hat as w times x, okay. So, just for this case I will make x as 4 cross 1, so that the 4 includes our bias unit also. So, you can write y hat as w x, x will be 4 cross 1, y will be 3 cross 1. So, if you want an appropriate w, please imagine what w should be. This should be 3 cross 4. In the general case, if y hat is k cross 1, where k is the number of classes and x is n cross 1, where n is the number of features, then w should have the size k cross n. Okay. Now, there are some people who will denote this w as w transpose, so as to be consistent with the notation I have used here. So, you might see this at multiple places. Sometimes you will see w x, sometimes you will see w transpose x, sometimes you will also see w transpose x plus b, where b is a vector, the vector of biases. Okay. So, just to clarify this notation for you, please notice if we remove the bias separately, this will become b 1, this will become b 2, and this will become b 3. B vector is separated and w x is separated in such notations. So, we will be using this kind of notation, as I said before, we will be using this interchangeably, especially when it comes to future videos and future weeks. Thank you. Welcome back. In this video, we will be looking at the basic idea of a biological neuron. The reason for talking about this is historical. As we saw in the last videos, when we look at the XOR gate, we required one extra layer between the input and the output in order to actually represent the XOR function accurately. Now, as it turns out, even before the XOR gate example, lot of people had the idea that if they could somehow replicate the functioning of a human brain, or at least of the neuron in the brain, that they could somehow replicate all of human thinking. Now, before I discuss the biological neuron, I will do it very briefly, but I want to point out that this analogy is, in my opinion at least, and in the opinion of Dr. Ganapathy also, it is not quite sound. Several people say this. Neuroscience is a completely different area, and even computational neuroscience is very different from what we do in actual neural networks, which you will be seeing in the next few videos. Computational neuroscience works on extremely complex phenomenon, and they try to replicate what we will be showing here far more accurately than what we will be doing. When we show the artificial neuron, which we will do in the next video, that is just going to be a toy case, and the reason why it works is basically mathematical rather than anything to do with a physical analogy between the brain and the neural network. Despite it being very popular in the media to talk about neural networks as if they were simulations of brains, and this is certainly a buzzword today, we think that this is not accurate, much like birds fly and aeroplanes are not actually trying to replicate what birds do. You know, you do not have flapping wing aircraft even today, but nonetheless you can take some inspiration from birds, but what you are looking at is the basic principle. Just like in the for bird flight or for aircraft flight, a basic principle is whatever lift that the wing generates has to be balanced by the weight of the body, whether it is an airplane or a bird. Similarly, we are trying to replicate some very rudimentary principles in learning, which is what we will try to do. So, to come back to a biological neuron, I am certainly not a biologist. So, this image roughly represents what happens in a biological neuron. So, this is the neuron cell at the cell body, and what happens whenever we get an input, whether it is through the eyes, which Dr. Ganapathy will be covering in detail in the next week, you know how our visual system works, but whether it is the eyes or your auditory system, finally when it goes to the brain, you actually have multiple source of inputs. Let us take the analogy of an eye, just like we in an image you have pixels, a lot of information comes from various sources. So, we can see input nodes, these are called dendrites. So, all these finally feed into one single neuron. Okay. It is possible that a single neuron can have as complex a feature a function as recognizing a specific face, say that of your mother or something of that sort. So, in that case you will get all these inputs from your mother's photo or from your mother's picture coming from each input cell. You can think of this as analogous to the features that we have in our usual diagram. Okay. And all these feed into one place. Now, when all of them feed into one place, we can think of that operation as if it is a summation. Okay. Now, what the neuron apparently does is, when all these come, the electrical signal either fires or it does not fire, okay, or it fires somewhere in between. Again, I am not a neuroscientist, so I am just going to give an approximate picture of what happens. So, now all these things come in, and then maybe below a certain threshold the neuron, so to speak, does not wake up, and above a certain threshold it wakes up, okay, or it fires. You can think of this as if somebody is shaking you in order to wake you up, and below a certain threshold, if they do it very lightly, you will not wake up, but if they shake you heavily, you will wake up. Similarly, the neuron activates only after a certain amount of electrical signal, all these inputs coming together activate it. You will notice that this picture is somewhat similar to the sigmoid that we had when we were dealing with logistic regression. Okay. So, as it turns out, these simple combination is what more or less defines a neural network. This is our abstraction or our cartoon picture of how a neuron works, which is lot of inputs come through the dendrites, they come into the neural cell, they sum up there, which we also did, whether we did it in linear regression or logistic regression, we sum it up, and then it either activates or it does not, or it activates intermediately, which is what we did with a sigmoid. Okay. Now, after that the output is called an axon. Now, the output could be single or it could be multiple, okay, depending on whether you have one class or multiple class when we are doing a neural network, and what connects it in between in neuroscience terminology is what is called the myelin sheath. What happens with myelin sheaths is that they get thicker and thicker as you generate memories which are stronger and stronger. That is, if you repeat an action, okay, whether it is writing, running, cycling, etc., this sheath tends to thicken as you do the same activity again and again. Now, all that abstracted out, what I want to point out is there is a simple abstract structure for this whole process, which is what we will be using for the rest of the course, which is that of multiple features as input coming up together, summing, and then you have some kind of activation. We will repeat this abstract picture in the next video, where we will look at the idea of an artificial neuron instead of a biological neuron. Thank you. In this video, we will be looking at the structure of an artificial neuron. So, the artificial neuron is a simple abstraction of a biological neuron. It is supposed to abstract out all the details that actually exist in the biological neuron and just give you whatever is usable. Please do remember that this is a simplification and this is not how actually our brain neurons work. In this video, the topics that we will be covering are what goes into an artificial neuron and the two operations. Really speaking, both of these operations were things that you had already seen within logistic regression. Okay. We also use these two in logistic regression. We are just going to formally combine these operations into a single thing called an artificial neuron. So, let us look at what an artificial neuron looks like in a neural network. So, suppose you have some inputs coming in from one end. We can call these biologically, these are supposed to be the equivalent of dendrites. So, you have some three variables, in general some vector x vector, which has these features x1, x2, x3. All these three come in, and as usual, as we did with both linear regression as well as classification, we simply take a linear combination. So, we do sigma wi xi, and this component we call z. Remember, the x that comes in is a vector and what comes out of this linear combination z is a scalar. Till this point, what we have here is essentially a linear combination. Now, this z goes into the next part, which is the nonlinearity, and what makes neural networks work really is this nonlinearity. One simple nonlinear function which we have already seen, for example, is the sigmoid function. Graphically, we denote it by the shape of the sigmoid curve. So, sigmoid of z would be 1 by 1 plus exponential z, minus z, which is the same as so we call this nonlinearity in general G. This might be the sigmoid. It could be other functions which we will see later, for example tan h. We also have another thing called the rectified linear unit or ReLU. So, any of these outputs, any of these nonlinearities could be used. Now, finally, after all this, what comes out is G of z. This is denoted by A, also labeled the activation. If this is the only thing in your network, then all you have is your prediction is simply the activation of this neuron, which is G of z. So, remember, the two portions of an artificial neuron are linear combination and an additional nonlinearity. In this video, we will look at a general version of the neural network called the feed-forward network. In the previous videos, we had seen what an artificial neuron was. A feed-forward network or a simple neural network, the term that you would have heard most commonly, is basically a collection of neurons. Each of these units here is a neuron. Now, each of these neurons or each of these layers, which are vertically concatenated, have a specific name. The very first layer is called the input layer. We had seen this during logistic regression, even in linear regression. So, you will have multiple features. This is the input vector. The intermediate layers here are called hidden layers. You could have multiple hidden layers. If the number of hidden layers is greater than 1, then it's called a deep network. Hence the name deep learning. So a deep network is simply a network with the number of hidden layers greater than 1. The final layer where you actually get the output you are interested in is called output layer. So you have our predictions, we have our predictions here, y1 hat, remember hat is used for predictions up till whatever is the number of classes that we are predicting for. Remember, k in general need not be equal to n, and in general each layer might have a different size. So these are the elements. Now each of these elements here is an artificial neuron. Okay. Technically speaking, we can even treat the input layers as if they were neurons, but generally it's only after the input layer that we look at each of these neurons and call them an artificial neuron. Remember that within each neuron we have two portions. We have a linear combination and we have a nonlinear activation function sitting there. Now, if I look at any neuron here, so for example this neuron, it has inputs coming from all the previous entities in the input layer. Okay. So for example, so this neuron here has n inputs plus, even though not explicitly shown here, you will have a bias unit which will be coming in here. So for this neuron you have n weights. From the input layer. So let's take a general neuron or a general set of neurons in some hidden layer. So let's say this is layer L. Okay. For example, this one would be layer 1, this one would be layer 2, hidden layer 1, hidden layer 2. Let's say we have layer L where all these neurons are there, and you have a prior layer. This is layer L minus 1. Let's say further that this layer had n neurons and this layer L has m neurons. So this means the total number of weights required, assuming every neuron is connected to every other neuron, would be n times m plus the bias units. Now, how many bias units do we have in such a case? Okay. Now, if I consider this neuron, for example, this takes input from all these n plus one bias. Now, if I take this one, it also takes all these n plus a different bias. Okay. So, each neuron gets a different bias. So, in this case, if we look at these m neurons, you have n times m, which are normal weights. The number of bias weights will be equal to m, okay, because each of these neurons has a different bias. So, the total number of weights in such a case is nm plus m. In a feed-forward network, all you need to do is you give all these xi's, if you give x vector and all the weights in every layer, we can find out y hat vector. Okay. So, this is called the feed forward process. Basically, you feed in the x, you also give all the w's of every single layer here, and simply by taking a linear combination, non-linearity, linear combination, non-linearity, linear combination, non-linearity, you can predict all the y. So, this is called the feed forward process. Such a network where all neurons are connected to every other neurons are called fully connected networks. In the general case, you need not always have all connections active. In fact, we will see later in convolutional neural networks that we have only some of these weights which are non-zero, and most of them are zero, which means each neuron is connected only to a few other neurons in the previous layer. So, that would be a special case, but in the most general case, you can think of a fully connected network, sometimes simply called FC network. The assumption behind the feed forward process is you know all the weights and you know all the input neurons. Later on, we will see when we come to back propagation how to actually determine these weights.